So we will get started. Let me share my screen here. So we have some things to finish up from Friday. So some more naming to do. And then we're going to get on to some calculations. Just as a refresher from what we did on Friday, we looked at naming ionic compounds. Remember, an ionic compound is made from a metal and a nonmetal, and two different ways to name ionic compounds depending if it forms only one type of ion or more than one type of ion. And just a refresher for that, let me check my pen to see if it's working. Hey, it's actually working today. So all metals in our group 1 here will always have a +1 charge. Group 2 metals, +2. Sc will always be +3. Silver, +1. Zinc, +2. Aluminum, +3. So your metals, those are the metals that will always have those charges. All other metals, the charges will be can be variable. So if it's a metal with only one charge, you just name the metal, and the non-metal, and you just add I to it. If it can form more than one type of ion, that's when we need our Roman numerals, so 2, 3, etc. Then we have our oxyions. So we have a polyatomic ion. They get special names as shown in the table here. Now, the next thing we're going to talk about are hydrated compounds. And a fair number of compounds in nature have water in them because water makes up, over 70% of the earth, right? Water's everywhere. So it makes sense that ionic compounds just are surrounded by water. And the way we name ionic compounds is the first part of the name is the same as any other ionic compound, but we add the word hydrate and a prefix in front of the word hydrate to say how many water molecules we have. And the prefixes are shown on this slide. And we'll use these prefixes for counting a lot of things in chemistry, but we have hemi, mono, di, tri, tetra, penta, hexa, hepta, octa, and goes on, nana, all that good stuff. One thing to note is that if you only have one water, you don't always have to say monohydrate. You can just say hydrate. A lot of the times mono is dropped, but if you have monohydrate versus hydrate, it really doesn't matter. But if we look at our compound here, we have barium chloride. Again, we don't need a Roman numeral here because barium, if you look on your periodic table, which I hope everybody has out in front of them, barium is element 56. Barium's in the second column, so this metal will always have a +2 charge. Since it always has a +2 charge, we don't need a Roman numeral. Remember, Roman numerals are only for metals that can have different charges. So this is barium chloride. We have 6 waters, so this is hexahydrate, as my dog goes crazy in the background. Okay, so what we're going to do here is we're just going to look at our elements and either write down the formula or give the name. So I'm going to give everybody a minute to do that while I go check on what's driving my dog nuts. So see if you can do A, B, C, and D. Send me a message if you have that. And so if you're completely stuck, not quite sure where to go, I will do A. If you're already working on A, great. So we have cobalt phosphate octahydrate. So the first thing we need to do is find cobalt. And what we'll see is that cobalt is element 27 and it is CO. So we write CO. Let me get my pen back out. So there's our cobalt. And now it's phosphate, so cobalt phosphate. Now we have to figure out how many cobalts and how many phosphates we want to put. So it's cobalt 2, so that means cobalt has a +2 charge. Phosphate, if we go look on the table here, phosphate is -3. And remember, when we have a metal and a nonmetal with different charges, we can just swap the charges with how many ions we have. So what I mean by that is that this will balance out charge-wise if we have cobalt 3, 2 phosphates. That's a neutral compound because the cobalts are giving a +6, the phosphates are giving a -6, and then octahydrate, 8 water. That's what octa means. So C, you can follow that to do B, C, and D. So I'll give everybody a few more minutes to do that. And if you have questions or you want to check, feel free to always message me because we do have a test next week, Wednesday. And so you can expect to see similar types of problems. So if you're not getting it, this is the opportunity to work on that. So B, if we look on B, we're looking for BE. This is beryllium. So beryllium. Now beryllium is in the second column, but it's the one odd molecule in that beryllium can have a +2 charge, but it can also have other charges. So beryllium is the only metal in the second column to need a Roman numeral. To figure that out, we look at how many chlorides there are. So chloride is -1. Chloride is is a halogen, so halogens are always -1. So we have 2 of them. So overall chlorine is -2. So beryllium, since we only have 1 copy, has to be +2. So that's beryllium 2 chloride dihydrate. What time will our test open? Your test will open at 12:01 a.m. on Wednesday and close at 11:59 p.m. on Wednesday, next week Wednesday, not this Wednesday. You have 1 hour to take it. As soon as you open it up, timer will start. If you get disconnected, timer's still going. So make sure you are somewhere with good internet. All right, so we have chromium 3 phosphate. So chromium is +3, phosphate is -3, not -1. So they're the same charge, so I only need 1 of each. Chromium is Cr, phosphate, PO4, trihydrate, 3 water. And then we have LiNO2. Li is lithium, column 1. I don't need a Roman numeral, lithium. NO2 is nitrite, and then hydrate. I will let you know what you need to get for the test later on in the week. It's still a week and a half away, so I will make that clear when it gets closer to that. Any questions about naming? Why don't I put monohydrate? Because for mono, you don't need to for the most part. You can, it's not wrong. I just like saving myself writing 4 letters. Monohydrate versus hydrate. Both are correct. Any other questions? Otherwise, we will move on. Okay. Next are our molecular compounds. Remember, a molecular compound is nonmetals only. And for this is relatively easy since we just did the prefixes for water. It's prefix, first element, prefix, second element, and the second element you add "ide." Here again, if you only have one copy, technically you could put mono. You don't need to. So for NI3, it's nitrogen triiodide. You could put mononitrogen triiodide. It's not incorrect. It sounds a little weird because most people don't have mono, but not incorrect. Same thing, phosphorus pentachloride, and P4S10 is tetraphosphorus decasulfide. So here I'm giving you 10 prefixes. Again, it could go higher, but we're only going to worry about 1 through 10. Mono, di, tri, tetra, penta, heta, hecta, opta, nana, deca. So let's do some naming here. So here I give you the names for the first one, and the other ones I give you the compounds I want the names. So some more practice. I will do the first one. Phosphorus trichloride. So phosphorus and phosphate are different. Phosphate is PO4. Phosphorus is the element. And this is relatively simple. It tells you right in the name what you have, right? So phosphorus trichloride, so PCl3, right? So this molecular compounds are way easier than ionic compounds because they're all the same. Molecular compounds are all the same. So see if you can do B, C, D, E, F, G, H. And while you do that, I'll tell you a fun little anecdote. So a while back, I want to say in the late 90s now, there was a girl, and for her science fair project, she was like in middle school. She went around to, I think it was like the California State Fair, and she wanted to ban the following compound. Monohydrogen dioxide. Monohydrogen dioxide, right? Because monohydrogen dioxide can be toxic if you have too much of it. It corrodes metal. It's acidic. It's found in baby food. It's found in a lot of toxic waste that companies will just put into the environment. And it can burn off your skin if it gets too hot. It's really a dangerous subject. You can drown in it, right? So she went to the California State Fair, got roughly 20,000 signatures of people wanting to ban monohydrogen dioxide. Or, sorry. It's dihydrogen monoxide. That's what it is. Got my story wrong. Dihydrogen monoxide, right? Yeah, so she got 20,000 people to sign ban dihydrogen monoxide. And this is just a good lesson that you should know a little bit of chemistry because dihydrogen monoxide, of course, is H2O. And H2O is poisonous if you have too much of it. It will burn off your skin if it's hot. It is found in baby food. It is found in a bunch of toxic chemicals. So that was just a fun little science project about chemistry literacy in the state of California, which apparently wasn't great because they got so many signatures. That's just your fun little chemistry story for today. So let's rattle these off relatively quickly because there's no really tricks to these. Chlorine monoxide, ClO. The hardest thing is probably just finding these elements on the periodic table if you're not used to them. But remember, for covalent compounds, they're all going to be in the top right because they're nonmetals. So disulfur, S2 tetrafluoride, F4. Phosphorus pentafluoride, PF5. CO would be our friend carbon monoxide. Can't smell it, can't taste it, but it will kill you. So make sure you have carbon monoxide detectors inside your house. Nitrogen. And if you take biochemistry, I will tell you why that will kill you. Nitrogen. Triiodide. Basically just latches onto a protein. So SiCl4, silicon. And that would be tetrachloride. And our last one is tetranitrogen. Tetraselenide, I believe. So again, molecular compounds naming, relatively easy, at least I think. Much better than our ionic compounds. Any questions about naming molecular compounds? Nope. It is relatively straightforward. All right. Let's move on to acids, though. Acids found in such things as pop, or as you call it in Texas, I believe that you say soda. Also, cleaning agents and vinegar. What is an acid? There are actually two definitions for acids. We're just going to go with the simple releases hydrogens, H plus in water. Technically, you never release just an H plus, but that's more for later on in the semester / Gen Chem 2. I'm not quite sure when we get to that. HCl is a very strong acid. It breaks down into H plus and Cl minus. That is, it ionizes. Basically, when you break down, if you make ions, that process is called ionization. And you can see next here, I have H plus AQ, Cl, AQ. Anytime you see AQ next to an element, that means aqueous. That means I'm dissolved in water. That's all aqueous means. And acids, they're sour tasting. Lemons, when you vomit, tastes very sour because your stomach is very acidic. It will dissolve metals eventually. And there are two types of ways we can name acids. One, if it's a binary acid or if it's an oxyacid. For binary acids, it's relatively simple though. You say hydro, name a nonmetal, ic acid. So that's why I said hydrochloric acid. So let's take a look at some of the naming, some practical things of this. Oh, first we have our oxy ions, I forgot. So oxyacids, they are, of course, harder to name. They get their own names. So what is an oxyacid? An oxyacid has one of our oxy anions that we introduced back in the polyatomic ions. And so for the names, if your oxy ion name ended in ate, so I'm looking at nitrate or sulfate, right? you just give it an ick plus acid. So that's why it's sulfuric acid. It's sulfuric acid because it has SO4, and SO4 is a sulfate, so we name it sulfuric acid. NO3 is nitrate, that's why it's nitric acid. While if it ends in an ite, if your polyatomic ion ends in an ite, you name it OS. So NO2 is nitrite, so it's nitrose acid. SO3 is sulfite, so it's sulfurose acid. Super confusing, I know. I've never thought of a good system for why 8 is ick and ite is os, but it is what it is. If stomach acid is around 2 pH, how come it doesn't eat us from the inside out? Because our stomach wall is, I believe, if I remember my biology right, is constantly like covered with like mucus and stuff. And so you have a protection from that. When you get an ulcer due to stress, among other things, that is basically your stomach starting to deteriorate a little bit. That's why it's like super painful. But yeah, we have protection like in mucus to help neutralize that acid in your stomach. That's why if you vomit a lot, your teeth eventually start to dissolve, which is not a good look. But yeah, so those are our oxyacids and how we name those. So of course, let's get practice. So remember, if it's just a element that contains hydrogen in one atom, we name hydroic acid. For poly or oxyion acids, we have naming systems based on it or ite. So I'll do A to just get us kicked off, right? So we have two elements, H and F. So that's hydro. And then we name fluorine, that's the nonmetal, but it's ic. So hydrofluoric acid. Yep. So go through the list, see if you can name them, following the naming scheme in the top right. When you do that, I'll tell you another one fun antidote. Those of you who have watched Breaking Bad, one of the ways they get rid of, let's say, competitors is through hydrofluoric acid. That's how they have dissolved some of the bodies. Fun fact, hydrofluoric acid is technically a weak acid. We do not consider hydrofluoric acid to be a strong acid. It is actually weak. But that is what they use to dissolve all the bodies in that show. It is very good at eating organic matter. But it is a weak acid. So let's see if we can get our other names here. Either name it or write it down for C and D. So I'll give everybody a minute or two to work through this. And while you're working, I'll give you another fun chemistry fact. Soda pop. If you take a tooth and put it in like Coca-Cola and just leave it there for like 2 weeks, the tooth will completely dissolve. That's how acidic Coke is. Yeah, that's just a fun fact. Coke can dissolve teeth, among a lot of other things. Seeing that Coke's actually a pretty good cleaner. So HCl, again, just follow from A. hydrochloric acid. See, working backwards, we have bromic. So your goal here is to figure out, what does brom refer to? That would be bromine. So hydrobromic acid is HBr. Then we have phosphoric acid. So we have something that ends in phosphoric. For that would come from phosphate, right? Anything that ends in an 8, we get that ic acid. And this is a oxyacid because there is no hydro in front of it, right? So if there's no hydro in front of the name, that means it's one of our polyatomic ions. So phosphoric acid, it comes from phosphate, H3PO4. Okay. How did I know there were 3 hydrogens, you might be asking yourself? 1, because I'm a genius. Just kidding. I've been doing this a long time. So phosphate has a -3 charge, right? Hydrogen will always have a +1 charge. When hydrogen's alone, it has a +1 charge. So to balance out the -3 charge of phosphate, because remember, when we make compounds, we generally want them to be neutral. I need 3 hydrogens to balance out that phosphate. So H3PO4. HClO2. So ClO2, if we go to our table, is chlorite. Since it ends in ite, we use ose. Horrible, I know. So this is going to be chlorose acid. So on the exam, would we be given something like table 3.4, or should we memorize that as well? My gut says you should probably know the oxyacids, right? Or sorry, the naming scheme of the polyatomic ions. So I think I'm going to go with that. You should be able to look at PO4 and say that's phosphate. So we're going to go with that for right now to know our table 3.4. Why don't you put hydro with E? Because it's a polyatomic acid. Hydro only goes if there's 2 atoms, like HF. Here we got more than 2 atoms. So you don't put hydro unless it is 2 atoms. NO3 is nitrate. So that's everybody's favorite nitric acid or nitric acid, depending on where you're from and how you pronounce things. Any questions about that? About naming our acids? So let me clear this then. And we're done with naming. Yay. So what we've just gone over Friday and today, any ionic compound, any molecular compound, and basically any acid in chemistry you can now name, and you can figure out the formula. So it is kind of fun next time you go shopping, look for these. And so now things that might have seemed like archaic, like this weird sounding name, now you can just say, oh, it's made out of these elements. I understand that now. So let me pull up the PowerPoint from today. Let me get that going. Let me pop that up. Okay, time for math. So we learned how to name everything. let's learn, using the periodic table, how I can determine the molar mass or the molecular weight of any element or any compound in the world. And really, all you do is that you add together the masses and the individual masses of the atoms. So let's see what I mean from that. So we have H2O. If you look in the periodic table, hydrogen is 1.01. Depending on the periodic table you have, it might be like 1.008. Any discrepancies like that on the test, like you're going to be so close that it's not going to make a difference in your calculation. So if you use 1.01 versus 1.008, you'll get the same answer more or less. Oxygen, 16. Again, some charts say 15.998 or 15.999, doesn't matter. Now, when you look up these masses on the periodic table, they have two different units, right? The first unit is grams per mole. So if you have 1.01 grams of hydrogen, you have exactly 1 mole of hydrogen. That's what that says. Or atomic mass units. And we talked about this already, but atomic mass unit, 1 AMU, is equal to 1 proton or 1 neutron, right? That's the weight of a proton or a neutron. So hydrogen has a proton. Oxygen is 16, so they have 8 protons and 8 neutrons, or 16 grams per mole. H2O, 2 hydrogens plus 1 oxygen. So you take 2 multiplied by the weight of hydrogen, because you have 2 hydrogens, and you add that to oxygen, because you only have 1 oxygen. So the weight of water is 18.02 grams per mole, or 18.02 AMU. So relatively simple to figure out the formula mass, or it's also called the molar mass, or it's also called the molecular weight of any molecule in the world. 18.02, not 33.01. I'm guessing you multiplied oxygen by 2 and added 1 hydrogen instead of multiplying hydrogen by 2 and adding 1 oxygen. Because if you do 32 plus 1, you'll get 33.01. Should be 18.02 though. 2 hydrogens plus 1 oxygen. So, of course, we're gonna do some practice. Now we know how to name everything, so I'm not just gonna give you the elements, like the symbols from now on. I'm gonna be throwing names at you. So I'll do A for us. Nitrogen dioxide. So the first thing you wanna do is write down, what is nitrogen dioxide? NO2, mononitrogen dioxide. Then you look on the periodic table, and you say, I have 1 copy of nitrogen multiplied by the weight of nitrogen. Nitrogen is 14.007. And I'm going to add that to now oxygen. I have 2 oxygens multiplied by, my periodic table says 15.999. And then you just do that math. And the weight of nitrogen dioxide is 56.005 grams per mole. That's the unit I will always use, probably moving forward. I'll always use the grams per mole, as we use that way more often. AMU, like I said in the previous slide, is a fine unit if you want to use it. Just as your friendly instructor, if you just memorize it as grams per mole, we're going to use that way more than AMU. So it's not 16 times 2. It's 16 plus 1.01 times 2, because we have 1 oxygen and 2 hydrogens. So you multiply based on how many elements you have. So 2 hydrogens, I multiply hydrogen by 2. 1 oxygen, I just leave it at 16 or multiply it by 1. But yeah, try to figure out the other ones. So B and C are determining the molecular mass. And then D, E, and F, we're going to use molecular masses to figure out some stuff. So I'll just do D because D is different. So D, what is the molecular mass of 72.1 millimolar SO2 if the molecular weight of SO2 is 60.47 grams per mole? So I hope everybody has been learning their metric units, because like I said, you need to know them for test 1, and we're going to use them all throughout this class. So if you still do not know them, you are behind, and so I would suggest that we do know them. So millimolar, there are 1,000 millimoles in 1 mole. So I started with the unit. I wanted to figure out the mass of 72.1 millimoles. So that's what I always start with in my train tracks. I want to get to grams. Grams is a weight, right? And my conversion from moles to grams is my molecular weight. So my first thing I did was get out of millimoles and just convert that to moles, which I did right here. So I converted millimoles to moles. Now, with my molecular weight, I can convert moles to grams. So 1 mole is 60.47 grams. My unit of moles have canceled out. My unit of millimoles is canceled out. I'm left with the weight of grams, multiply across, that's 4.36 grams. All right, so let's see if we can do B, C, E, and F. As always, please let me know if you have questions. Not sure what to do, anything like that. I am here to help you. That is what I get paid for. So lead 4 chloride. First thing, just figure out where they are in the periodic table, right? So lead is element 82. Chlorine's element 17. Now we have to figure out what the ratio is. Chlorine's a -1 charge. Lead's a +4 charge. And you know it's a +4 because it's lead 4. You know chlorine is -1 because chlorine's always -1. It's a halogen. So to make this balance, I need 4 chlorines for every 1 lead. Overall, now the charges are +4 and -4, which equals 0, which is what I want. So lead 4 chloride is PbCl4. Once you have that down, getting the weights is relatively easy, right? You just look at your periodic table. Lead is 207.2 plus now 4 chlorines, right? So 4 times chlorine is 35.453. And so lead chloride is 349.012 grams per mole. So C now. C gets a little trickier because we have parentheses, but we already did problems in class to figure out, what to do with that parenthesis. And just remember, you distribute the 2 to everything inside the parentheses. So CaNO3 2, calcium, element 20. So we have 1 calcium, and the weight of calcium is 40.078 plus, well, we have 2 nitrogens. So that's 2 times 14.007 plus 6 oxygens. So 6 times 15.999. Again, if your periodic table says 16, that is fine. Add them all together, you get 164.086 grams per mole. So is there any questions about how to determine the molecular mass of A, B, or C? How to get any element's molecular mass using the periodic table? Okay, let's do some conversions. Spent about 2 weeks at the beginning of this class doing conversions. Hopefully some of that stuff stuck. Now we're going to use it in chemistry terms. The number of molecules in 55.93 kilograms HCl, hydrochloric acid. Hydrochloric acid has a molecular weight of 36.46 grams per mole. Okay, so I want molecules, and I start with kilograms. One good thing to do before you put in any numbers is just figure out what the conversion is going to be. So I know overall I want to go from kilograms to molecules. So I'm going to set up my train tracks and just, without any numbers, just figure out what's going to happen. So I start in kilograms, which is a weight. The only way to go to molecules is by using moles. Moles are the only ways to go to molecules. I can't go from grams to molecules. I don't have a conversion for that. But I do have a conversion from moles to molecules. If you remember, we call that Avogadro's number. So I'm going to write Avo's number here. So my first task is to go from a weight, which is kilograms, to go to moles. I do have a conversion here that'll tell me how to convert between grams and moles of hydrochloric acid. But it's grams, but I'm in kilograms. So my first thing I need to do is to convert kilograms to grams. Once I do that, I'm in a unit of grams. Once I'm in a unit of grams, I can convert to moles. So grams cancel out, I'm in moles. And because of Avo's number, I can go from moles to molecules. So I think that's, to me, I think that's really good practice, and that will actually show you if you completely understand unit conversions. If you can figure out the path without putting numbers in. But we have our path now, let's put in the numbers. So we start with 55.93 kilograms. For every 1 kilogram, there's 1,000 grams. For hydrochloric acid, for every 36.46 grams, we have 1 mole. For every 1 mole, Avogadro's number is 6.022 times 10 to the 23 molecules. That's not something you memorize. I will give you that on the test. That's a constant. And I did not calculate that for some reason. But that is how you set that up. Let me calculate that really quick because I know I'm going to be asked that question. If I don't, what's the answer? So 5.93 times 1,000 times. That is 9.238 times 10 to the 26 molecules. 9.238, 1026. So big number. Don't be shocked by big numbers in this class. We're going to get big numbers. Last thing we need to do is F. So let's do that really quickly. The mass in grams, actually, sorry, for those of you so right, I can do that above everything. The mass in grams of 5.24 times 10 to the 24th NaHCO3 atoms with that molecular weight. F is the exact reverse of E. In E, we started in kilograms and we wanted to go to molecules. F, we're starting in molecules and we want to go to grams. So same logic, but reversed. Since class is almost up, I'm just going to go straight to the numbers though. But hopefully looking at E, you can already kind of visualize how to go from molecules to grams. So we have 5.24 times 10 to the 24 atoms or molecules. Same, more or less the same thing, but I guess I'll be consistent. Molecules. There are 6.022 times 10 to the 23rd molecules and 1 mole of anything. And for our compound, we want to end in grams. So our molecular weight is 1 mole of NaHCO3 is 84.01 grams. Moles cancel out, molecules cancel out. I'm left with a weight in grams, which if I did my calculation correctly, should be 731 grams. And that is how we can use molecular weight. 1, how to determine molecular weight. And 2, how we use molecular weight in calculations to figure out, moles or to figure out grams, figure out atoms. So just as a reminder, the 3 major units we usually focus on in chemistry are either grams, moles, or atoms. The switch between grams and moles, that's our molecular weight. The switch between moles and atoms, that's Avogadro's number. That's how we can convert anything from a gram to a mole or to atoms, as long as we have those things. But any questions about the calculations shown here? Doesn't look like so, or if you are, you're still typing. That's all the time we have, so I'm going to clear all this. Again, thank you all for coming and listening. I hope you learned something interesting, or if not interesting, hope you learned something. I will post this online as always. Looks like we do have a question. I'll just thank you. You are very welcome. I will post this online as always. For F, you make it 52.4. Make it 52.4. So is it the same power as Avogadro's number, right? You could make it 52.4, so it's the same power as Avogadro's number. I don't. I just put it in the calculator. The person who just privately messaged me, your name to me is iPhone, so I'm not sure who you are, so send me an email. Or I guess just tell me your name. Otherwise, I will catch everybody later. I will put up a homework as always. The homework is due on Sunday as always. But otherwise, have a good day. Hope everybody has a good one.